Implicit differentiation is one of the more tricky topics in calculus, maybe even the hardest, but it really doesn't have to be. So in this video, I'm going to show you the one trick I always use on implicit differentiation problems to make them so much easier. It'll really help you kind of conceptualize what you're doing and show you how to keep these problems straight. So without further ado, let's go ahead and jump right into it. So here's the problem we're going to be doing today. We're going to use implicit differentiation to find an equation of the tangent line to the curve at the given point. Our curve is going to be x squared plus xy plus y squared equals 3, and our point is 1, 1. So I told you I was going to show you the one trick I use to make these implicit differentiation problems as easy as possible, and that trick is this. The first thing you want to do when you're doing these problems is figure out, and maybe even write down, which letter in your curve represents the variable and which letter represents a function. That's going to determine exactly how you treat each of these pieces as you take the derivative in your implicit differentiation. So what I mean by that is typically when you're given some curve that is relating x and y, like this in this case, your x is going to be your variable usually, and then y is going to be the output, which means it's a function. So I would even write that down. Just start out by saying x is a variable and y is a function. Whatever your input is your variable. Whatever your output is your function. Typically, this is the way that we see x's and y's represented. If there was some sort of context that made it different, you would want to be aware of that. But in this case, since they don't tell you, we can kind of assume the standard definition for what's a variable and what's a function. So the reason why this is important is as we go through and take the derivative of this function, which is what implicit differentiation is, it's really just taking a derivative, you're going to take the derivative with respect to whatever your variable is. Since x is our variable, we're going to take the derivative with respect to x. And we're going to do the derivative with respect to x on both sides of this equation. So to do that, we can kind of go through term by term. So first of all, we're taking the derivative of x squared with respect to x. Well, since x is a variable, the important thing to keep in mind here is the derivative of x is just 1. The derivative is going to behave the way that you expect it to work when the thing you're taking the derivative of only has your variable in it. So the derivative of x squared we can do using power rule. It's just going to be 2x, right? That's pretty straightforward. The tricky part comes into play when you have x's and y's, and so in this case we're taking the derivative of x times y. Well, we have now our variable and our function. Well, we have the product of x times y. So since we're taking the derivative of something that is a product, we're probably going to want to use the product rule. So let's kind of make a side problem of that over here. So if we're taking the derivative with respect to x of x times y, product rule says that we basically want to figure out, first of all, which function we're going to call f and which function we're going to call g. Let's just say x is going to be f, y is going to be g. It doesn't really matter which one you pick. You're just going to pick x for one and y for the other. And then you want to figure out y or f prime and g prime. So this is where this distinction of variable versus function really comes into play. Because when we take the derivative with respect to x, with respect to our variable, whatever our variable is going to work the way that you expect derivatives to work. The derivative of x is just 1. But when you're taking the derivative of x, or I'm sorry, when you're taking the derivative with respect to x of the letter that you decided is your function, in this case y, it's not going to work the way you expect. The derivative of y is not just going to be 1 because it's not a variable, it's a function. So what you have to keep in mind is the derivative of your function, you're not really going to know. And that seems weird, I know. It makes it seem like these problems are impossible, but they're not. Keep in mind that y is a function that we don't know. We don't know what y is. We don't have, y equals some function of x. It's not given to us. So as a result, you can't really know the derivative of y if you never knew y in the first place. So what we can do, instead of actually trying to find some derivative, is to just say the derivative of y is just the derivative of y with respect to x. dy dx literally just means the derivative of y with respect to x. If you don't know y, you can't know its derivative. But this symbol here literally just means the derivative of y. So now what we can do is use the product rule to multiply f prime times g, g prime times f, and then add those together. So that'll give us 1 times y is y, plus x times dy dx. So this is the derivative of x times y with respect to x. So we'll just go ahead and kind of put this over here back into our main problem. And then we want to find the derivative of y squared. And again, we're doing this with respect to x. So that's again where this one trick I'm trying to tell you comes into play. Our function is y, so we cannot just use the power rule here. We could only do that when we had our variable, but when we have a function raised up to a power, now we have to do chain rule because we have this inner function here being raised up to a power. So we have a function within a function, a composite function. So using the chain rule says we're going to take the derivative of our outside function, which is the squared piece, and we're going to leave the inside function alone. So we're going to bring the power down in front, leave our inside function alone, and then raise or lower the power down to 1. So y to the first is just y. And then we're going to multiply this by the derivative of our inside function. Well, just like we did over here, the derivative of y with respect to x is just dy dx. And then the derivative of a constant, 3, is just going to be 0. So now what we want to do is solve for our dy dx. And the reason we're solving for dy dx is dy dx represents the slope of our function y. Well, the slope is necessary in order to figure out the equation of a tangent line. A tangent line is going to have a specific slope, and it's going to go through a specific point. We already know the point that it's going to go through, but we need to figure out its slope, which is exactly what dy dx represents. So all we have to do now is isolate dy dx. To do that, we can subtract over these other terms that don't have dy dx in them to the other side of the equation. And then once we've completely separated our dy dx and our non-dy dx terms, we can factor a dy dx out of this side of the equation that does have dy dx on it. And then to get dy dx all by itself, now that we only have a single dy dx, we can divide over this other piece to the other side of the equation. And now that we've solved for dy dx, we need to figure out the slope of this function at the specific point. Because when we're trying to find a tangent line to an equation, that tangent line, it always needs to share a specific point with your function, which we already know is going to be 1, 1. They told us that's the point we're using. And we also can figure out by plugging 1 in for x and 1 in for y into this equation, we can figure out that 1, 1 does lie on this curve. And not only do they need to share a point together, they also need to have the same slope at that point. So what we need to do is figure out the slope of our function y at the point 1, 1. So to do that, we figure out our dy dx and we just have to plug in 1, 1. So doing that is going to give us negative 2 times 1, which is negative 2, minus 1, over 1 plus 2 times 1, which is 1. And I'm sorry, that was supposed to be a 1. Negative 2 minus 1 is negative 3. 1 plus 2 is 3. So the slope that we want to use is negative 1. So now what we can do is use the generic form of a line, the generic equation for a line, which is y equals m times x minus x0 plus y0. Our tangent line equation should look something like this, because this is what the equation of a line looks like. M is always going to be your slope. We just figured out using dy dx that our slope is going to be negative 1. X is our variable, and then our x0 is the x-coordinate of the point that we know this line has to go through. Well, we know it has to go through the point 1, 1, so we can use 1 as our x0 and 1 as our y0, because that's the x and the y coordinate. So doing that gives us 1 for x0, 1 for y0, and then we can simplify this. So negative 1 times x is negative x, negative 1 times negative 1 is positive 1, plus another 1, which just tells us that the equation of this tangent line, which goes tangent to this curve and through the point 1, 1, is just going to be y equals negative x plus 2. Hopefully you found this video helpful. If you did, please be sure to hit that thumbs up button down below. It's a huge help to my channel so I can keep making more videos like this. If you want to see some other implicit differentiation problems, go ahead and click on one of those right over there on the other side of your screen. And be sure to hit that subscribe button and the bell icon as well. I've got some more implicit differentiation problems coming out in the coming weeks. You don't want to miss those. So see you next time. Thanks.